Tonight, we're going to talk about the most dangerous object in the known universe. And it's not a black hole. You've heard the warnings about black holes, the point of no return, the crushing gravity, the thing that swallows light itself. But here's what almost nobody tells you. A black hole, sitting quietly across the galaxy, will probably never hurt you. You'd have to go to it. It doesn't come to you. There's something else out there that already has. On December 27, 2004, a dead star released more energy in 0.2 of a second than our Sun produces in 250,000 years. That energy crossed 50,000 light-years of empty space, hit Earth's atmosphere, and measurably disturbed our planet's magnetic field. Nobody saw it coming. Nobody could have stopped it, and almost nobody on Earth even noticed. That object is called a Magnetar, and by the end of tonight, you'll understand exactly why it deserves more of your fear than any black hole ever will. Before we get into it, if deep space mysteries like this keep you up thinking, take a second to like this video or subscribe. It helps this channel reach more curious minds like yours. Now, let's begin. To understand why a Magnetar is so dangerous, you first need to understand what it actually is. Not a planet, not a star in the way the Sun is a star. Something stranger, something that shouldn't be able to exist by the rules of everyday physics, and yet does. Every Magnetar begins the same way every neutron star begins, with a massive star living out its final moments. Not stars like our Sun. Our Sun is too small, too lightweight to ever become what we're about to describe. The stars that end this way are giants, at least 8 times the mass of the Sun, often far more. For millions of years, these stars burn through hydrogen, then helium, then heavier elements, layer by layer, fusing matter in their cores to hold themselves up against their own gravity. It's a war that never stops, gravity constantly trying to crush the star inward, fusion constantly pushing back outward. For most of a star's life, the two forces balance, but eventually the fuel runs out. The star reaches iron in its core, and iron can't be fused for energy. The outward pressure disappears almost instantly, and gravity, which has been waiting this entire time, wins. The core collapses. Not slowly. In less than a second, a region of the star, roughly the size of the Earth, crushes itself down to something about 20 kilometers across. That's the width of a small city. All of that mass compressed into that tiny space. The outer layers of the star, meanwhile, are blasted outward in a supernova, one of the most violent explosions in the universe, briefly outshining entire galaxies. What's left behind, sitting at the center of that explosion, is the object we're interested in tonight. A neutron star. Here's where things stop making intuitive sense. A neutron star packs roughly 1.5 times the mass of our entire Sun into a sphere about 20 kilometers wide. To put that in perspective, if you could somehow scoop out a single teaspoon of neutron star material and bring it to Earth, that teaspoon would weigh about 1 billion tons, roughly the same as a mountain. Not metaphorically, literally, 1 billion tons in a teaspoon. How is that even possible? Normal matter is mostly empty space. Atoms are made of a tiny, dense nucleus surrounded by electrons, orbiting at relatively enormous distances. If you removed all the empty space inside the atoms that make up your body, you would shrink down to roughly the size of a grain of dust, while keeping all your mass. That's how much empty space ordinary matter actually contains. Inside a neutron star, that empty space is gone. The collapse is so violent, so total, that electrons get crushed directly into protons, transforming them into neutrons and releasing a flood of neutrinos in the process. The star becomes, almost literally, a single giant atomic nucleus, roughly 20 kilometers across, held together not by chemical bonds or electromagnetic forces, but by something called neutron degeneracy pressure. This is a purely quantum mechanical effect. It's the same principle that prevents you from pushing your hand through a table. Neutrons, once packed close enough together, simply refuse to occupy the same space. That refusal, multiplied across an entire stellar core, is strong enough to halt a collapse driven by a force as powerful as gravity. It is, for most neutron stars, the last line of defense between a stable dead star and complete collapse into a black hole. And these objects don't just sit still. Neutron stars spin. Before collapse, the star's core was already rotating, slowly, the way our sun rotates. But angular momentum has to be conserved. When something the size of the Earth collapses down to the size of a city, that same rotational energy gets concentrated into a vastly smaller space. The result is spin speeds that sound impossible. Some neutron stars rotate hundreds of times per second. Imagine an object more massive than the Sun, spinning faster than a kitchen blender. Many neutron stars are also pulsars. As they spin, beams of radiation shoot out from their magnetic poles, sweeping across space like a cosmic lighthouse. If one of those beams happens to sweep across Earth, our telescopes detect a precise, rhythmic pulse. That's actually how neutron stars were first discovered, in 1967, when a graduate student named Jocelyn Bell Burnell noticed a signal so regular, astronomers briefly joked it might be aliens. It wasn't aliens. It was a spinning neutron star, ticking like a clock built by nature itself. Now here's the important distinction for tonight. Every magnetar is a neutron star, but not every neutron star is a magnetar. Most neutron stars have powerful magnetic fields, by any normal standard, fields that would already dwarf anything humans have ever built. But a small fraction of neutron stars, somewhere around 1 in 10, end up with magnetic fields so extreme, so far beyond their siblings, that they get their own name entirely. These are the magnetars, and what separates them isn't their mass. It isn't really even their size. It's something invisible, something that doesn't announce itself with light the way a black hole's silhouette does, but which may be the single most destructive force tied to any compact object in the known universe. That's what we need to understand next. Not what a neutron star is, but what makes a magnetar different from every other dead star in the galaxy. So what actually separates a magnetar from an ordinary neutron star? The answer comes down to one thing: magnetic field strength. And once you understand the numbers involved, you'll start to see why scientists treat these objects with a level of caution usually reserved for black holes, despite the fact that a magnetar has no event horizon, no point of no return, nothing that swallows light. It doesn't need any of that to be dangerous. Let's start with something familiar. Earth has a magnetic field. It's the reason compasses point north, the reason auroras appear near the poles, the reason your phone has a working compass app at all. Earth's magnetic field is measured at about half a Gauss. That's the unit scientists use for magnetic field strength. Half a Gauss. Weak enough that you'd never feel it, strong enough to shield our entire planet from a constant stream of dangerous particles from the sun. Now think about the strongest magnet you've personally encountered. An MRI machine in a hospital uses a magnetic field of roughly 1 to 3 Tesla, which converts to about 10,000 joules to 30,000 Gauss. That field is strong enough that loose metal objects, scissors, oxygen tanks, anything magnetic, can become dangerous projectiles if brought too close. Hospitals run entire safety protocols around this. People have died because a metal object got pulled into an MRI machine at speed. The strongest sustained magnetic fields ever created in a laboratory on Earth reach into the range of a few 100,000 Gauss, achieved only briefly with enormous amounts of energy, using specialized equipment most people will never see in person. A magnetar's magnetic field is measured not in thousands of Gauss, not in millions, but in quadrillions. A typical magnetar has a magnetic field of around 1 quadrillion Gauss. That's a 1 followed by 15 zeros. To put that in a single comparison, a magnetar's magnetic field is more than 1,000 trillion times stronger than Earth's. Not 1,000 times, not 1,000,000 times, 1,000 trillion times. Numbers at this scale stop feeling like numbers and start feeling like nonsense. So let's slow down and make this tangible. If a magnetar somehow ended up positioned around halfway between the Earth and the Moon, its magnetic field would be strong enough to disrupt the magnetic strip on every credit card on the planet. It would wipe digital data from every hard drive on Earth. It would distort the electromagnetic signals our nervous systems use to function, because your body, every human body, runs on bioelectricity. Nerve signals are electrical. Muscle contractions are triggered electrically. A field that powerful doesn't just interfere with your electronics, it interferes with the basic electrical processes keeping you alive. And it goes deeper than biology. At magnetar-level field strengths, the field becomes strong enough to distort the actual structure of atoms. Under normal conditions, electrons orbit an atom's nucleus in roughly spherical patterns, the basis for all of chemistry as we know it. Inside a magnetic field this extreme, those orbits get crushed and elongated into thin cigar shapes, stretched along the direction of the magnetic field. The chemistry you depend on, the chemistry that builds proteins and DNA and every molecule in your body, simply stops working the way it's supposed to. At magnetar field strengths, ordinary atoms become something else, something physics has a name for, but biology has no use for, because nothing alive could survive in that state. So where does a field this powerful even come from? The leading explanation traces back to a theory proposed in 1992 by astrophysicists Robert Duncan and Christopher Thompson. Their idea centers on the moments right after the supernova, when the newborn neutron star is still blisteringly hot and spinning at incredible speed, sometimes completing a full rotation in under a few milliseconds. Inside this newborn star, hot plasma churns and convects, similar to the way fluid moves inside a pot of boiling water, except this fluid is electrically charged, and the star is spinning faster than almost anything else in the universe. That combination, fast rotation plus violent internal convection of charged material, can act like a dynamo, the same basic mechanism that generates Earth's magnetic field, except operating at an intensity almost impossible to comprehend. If the timing and the physical conditions line up just right, this dynamo can amplify the star's magnetic field by a factor of 1,000 or more compared to an ordinary neutron star, locking in a magnetic field so powerful it will take thousands of years to meaningfully decay. This detail matters because it means a magnetar isn't a different kind of object built from different physics. It's what happens when a neutron star's formation goes through a narrow window of extreme conditions, spinning just fast enough, churning just violently enough to lock in a magnetic field at the absolute upper limit of what nature seems to allow. And here's the part that should genuinely unsettle you. That field doesn't need contact, it doesn't need impact, it doesn't need the object to come anywhere near you in any conventional sense. A black hole's danger is fundamentally about proximity. You have to get close to its event horizon before its gravity becomes lethal. And that boundary, while invisible, is sharply defined and physically small. A magnetar's danger radiates outward through empty space, through its magnetic field, and through bursts of radiation, in ways that can be felt from staggering distances. Distances measured not in kilometers, but in light years. We're about to see exactly how far that danger can reach. Because on December 27, 2004, we found out. Not in theory, not in a simulation, in reality. A magnetar tens of thousands of light years away released a burst of energy so powerful that it reached Earth, passed through our atmosphere, and left a measurable signature on our planet's magnetic field. That event is where we're going next. Most people have never heard the name SGR 180620. There's no movie about it, no headline that's stuck in public memory the way headlines about asteroids or black holes do. But on December 27, 2004, this object did something that, for 0.2 of a second, made it the brightest thing in our sky outside of the sun and moon. Brighter, for that brief instant, than every star, every supernova, every cosmic event ever recorded by human instruments up to that point. SGR 180620 is a magnetar. It sits in the constellation Sagittarius, somewhere between roughly 30,000 and 50,000 light-years from Earth, depending on which measurement method astronomers use. For context, that distance is so vast that even traveling at the speed of light, the fastest anything in the universe can move, it would take tens of thousands of years just to get there. This isn't a neighboring star. It's not even in our cosmic backyard. It sits on the far side of the galaxy, buried in the crowded, dust-choked region near the galactic center, a part of the sky so dense with material that it's notoriously difficult to study at all. Astronomers had been watching SGR 180620 for years before that day, ever since its discovery in 1979. It belonged to a category of objects called soft gamma repeaters, magnetars that periodically release small bursts of gamma rays, sudden tiny eruptions caused by stress fractures in the magnetar's crust. Over the decades, it had produced over 450 of these smaller bursts. Astronomers understood it as an active, occasionally unpredictable object, but nothing in its history prepared anyone for what happened on December 27th. In a fraction of a second, less than 0.2 of a second, SGR 180620 released an explosion of energy that astrophysicists later calculated at roughly 10 to the power of 46 ERGs. To understand what that number means, consider this comparison made by the scientists who studied the event. In that fifth of a second, the magnetar released as much energy as our sun produces over about 250,000 years. Not 250,000 watts, not 250,000 times the sun's daily output. The total energy our sun generates across 2,500 centuries, released by a dead star in roughly the time it takes you to blink. This single flare released roughly 100 times more energy than the only two previous giant flares ever recorded from Magnetar. One observed in 1979, another in 1998. It instantly became, and still remains, the most energetic explosion of its kind ever directly measured by human instruments. And it didn't stay contained to deep space. The burst of gamma rays and X-rays crossed tens of thousands of light years, swept through our solar system, and slammed directly into Earth's upper atmosphere. Within moments, instruments across the planet detected something was wrong. The flare ionized our upper atmosphere so strongly that it temporarily inflated the ionosphere, the electrically charged layer that sits roughly 60 to 600 kilometers above Earth's surface. Researchers later found that the ion density at an altitude of 60 kilometers changed by 6 orders of magnitude. That's not a small fluctuation. That's the atmosphere's electrical structure being measurably rewritten for a brief period by an object on the opposite side of the galaxy. Satellites picked up the disturbance immediately. Detectors that were never designed to study Magnetars, spacecraft built for entirely different missions like RESI and the Geotail satellite, recorded the event because the burst was simply too powerful to miss, even with instruments pointed in other directions for other purposes. Earth's own magnetic field registered a detectable signature from the event, later confirmed by researchers studying data from near-Earth satellites. An object 50,000 light-years away left fingerprints on our planet's magnetosphere. No satellites were destroyed, no power grids failed, no one on Earth experienced any direct physical harm. From this distance, the event was, in the words of one of the astronomers who studied it, fascinating and faintly humbling rather than dangerous. But here's the sentence that should sit with you for the rest of this video. Dr. Brian Geinsler, one of the lead researchers studying the flare, said this about the event. Had it happened within 10 light-years of Earth, it would have severely damaged our atmosphere. 10 light-years. Read that again. Not 10,000, not 1,000. 10. An object that, from 50,000 light-years away, still managed to physically disturb our planet's ionosphere and magnetic field, would have stripped away meaningful amounts of our protective atmosphere if it had been positioned merely 10 light-years from Earth instead. For comparison, the nearest star system to our own, Alpha Centauri, sits about 4.4 light-years away. 10 light-years would put a magnetar of this power roughly within our closest cluster of stellar neighbors. Close enough that, on a galactic scale, we would consider it essentially next door. Geinsler followed that warning immediately with a piece of reassurance. None of the known magnetars capable of producing a flare this powerful sit anywhere near that close. The nearest ones we've found are thousands of light-years away, distances Geinsler himself described as, quote, a very safe distance. And we'll spend real time later in this video examining exactly how safe that distance actually is, and what it would take for that safety margin to ever change. But before we get there, sit with what actually happened on December 27, 2004. A star most people will never hear about, sitting on the far side of our own galaxy, released more energy in 1/5 of a second than our Sun produces in 250,000 years. And that energy reached out across an almost incomprehensible gulf of empty space and touched our planet. Not in theory, not in a computer model, in recorded, measured, peer-reviewed reality. A black hole could never do this. A black hole sitting 50,000 light-years away does essentially nothing to Earth, because a black hole's danger is gravity, and gravity at that range is functionally meaningless. A magnetar's danger isn't gravity. It's an active, eruptive force that radiates outward through space itself. And that single distinction is the foundation of everything we're about to explore next. When we ask a far more unsettling question, what would actually happen if an event like this occurred not 50,000 light-years away, but far closer to home? So far, everything we've covered is real, measured, documented history. A magnetar 50,000 light-years away genuinely disturbed Earth's atmosphere and magnetic field in 2004. Now we're going to do something different. We're going to use real physics to walk through what would happen if an event like that occurred much closer to home. Not science fiction, not exaggeration. The same equations astrophysicists use, applied to shorter distances. The key concept you need to understand first is called the inverse square law. It's a simple but brutal piece of physics that governs how radiation spreads through space. When energy radiates outward from a point in all directions, like light from a bulb or gamma rays from a magnetar flare, that energy spreads across an ever-expanding sphere. As the radius of that sphere doubles, the energy gets spread across 4 times the area, meaning the intensity at any single point drops to 1/4. Triple the distance, and intensity drops to 1/9. The relationship isn't linear, it's squared, and it cuts both ways. Move an object twice as close, and the energy you receive doesn't double. It quadruples. Move it 5 times closer, and the energy increases 25-fold. This is the exact math one astronomer used when explaining magnetar danger. If a magnetar were 1/5 the distance of another, the impact on Earth wouldn't be 5 times stronger. It would be 25 times stronger. This is why distance, in the context of magnetars, isn't just a number on a scale. It's the single factor separating scientifically fascinating from civilization ending. Let's apply this. We know that a flare at 50,000 light-years measurably disturbed Earth's ionosphere and magnetic field, with no real danger to life. We know that astronomers calculated that the same event at 10 light-years would have, in their own words, severely damaged our atmosphere. Let's go even closer than that, because once you start walking this distance down toward zero, the consequences escalate fast. At around 10 light-years, the primary danger is atmospheric. The flood of gamma rays and X-rays striking the upper atmosphere would trigger a cascade of chemical reactions, breaking apart nitrogen and oxygen molecules and producing nitrogen oxides in large quantities. These compounds are extremely effective at destroying ozone. Researchers studying this exact scenario, motivated partly by trying to explain ancient mass extinction events, have estimated that a giant flare at this kind of range could destroy a significant percentage of Earth's ozone layer, potentially as much as 30 to 40% within moments. The ozone layer is what blocks the bulk of the sun's ultraviolet radiation from reaching the surface. Damage it severely enough, and ordinary daylight becomes hazardous to every exposed organism on the planet, contributing to cascading ecological collapse, crop failure, and a measurable rise in radiation-related illness across the surface world. Move the hypothetical source closer still, down to 1 or 2 light-years, somewhere within what astronomers consider our closest stellar neighborhood, and the danger profile changes completely. At this range, the initial gamma-ray pulse alone would deliver a radiation dose strong enough to be a direct hazard to unshielded life. The atmosphere would still absorb much of the initial blast, sparing the surface from instant lethality, but the secondary effects would be devastating. The flare's energy interacting with atmospheric nitrogen would produce a thick haze of nitrogen dioxide, a reddish-brown gas that can block significant amounts of sunlight, potentially triggering rapid surface cooling, not unlike the climate disruption following a major asteroid impact or supervolcano eruption. Within hours, satellites in orbit, anything not shielded against radiation, would be permanently disabled. Power grids on the side of Earth facing the burst would experience the kind of geomagnetically induced surges that, on a smaller scale, have already knocked out electrical infrastructure during severe solar storms. Except this would be far more sudden, far more intense and impossible to forecast in advance. Because unlike solar flares, which the sun gives us hours or days of warning, for a Magnetar's giant flare arrives with no warning whatsoever. Light speed is the only signal. By the time you detect it, it has already arrived. Now go further still. Imagine, purely hypothetically, a Magnetar positioned somewhere inside our own solar system, at a distance comparable to the outer planets. At this range, we're no longer talking about atmospheric damage or electrical grid failures. We're talking about an object whose magnetic field, that 1 quadrillion Gauss field we discussed earlier, would begin to interact directly and violently with the magnetic fields of every planet it passed near, distorting orbits over time, stripping away planetary atmospheres not protected by a strong magnetic field of their own, and irradiating anything in its vicinity with a level of high-energy particles that would make long-term survival on any nearby world essentially impossible. It's important to say clearly that this entire progression from 10 light-years down to inside the solar system is not a prediction. It is not something astronomers believe is likely or even remotely probable, given everything we currently know about where Magnetars exist in our galaxy. We'll get to exactly how unlikely this is, and why, later in this video. What this section demonstrates is something different. It demonstrates the mechanism. It shows you, using real physics and real published research, exactly how an object with no event horizon, no visible danger zone, nothing that swallows light, can still pose a threat that scales from measurable curiosity to extinction-level event, purely as a function of distance. A black hole's threat is defined by a boundary. Cross it, and you're in danger. Stay outside it, and at almost any reasonable distance, you are completely safe, because gravity weakens with distance just as predictably as everything else in physics. A Magnetar's threat doesn't have a clean boundary like that. It has a gradient, a spectrum. It begins disturbing satellites and ionospheres from 50,000 light-years away, and it would still be disturbing them, just exponentially more violently, at every single distance closer than that. There is no safe radius around a Magnetar in the way there's a safe radius around a black hole. There's only a question of how much damage occurs at any given range. And that distinction is exactly why, when you actually sit down and compare the two side by side, the case for fearing Magnetars more than black holes becomes far stronger than most people expect. That's where we're headed next. Let's put these two objects side by side and judge them honestly, not based on reputation, not based on how many movies have been made about each one, based on actual physics, actual risk, and actual behavior. Because once you do that, the case for fearing Magnetars more than black holes becomes surprisingly easy to make. Start with black holes. A black hole's danger is, in a strange way, one of the most honest dangers in the universe. It has a boundary called the event horizon, a precise, mathematically defined point beyond which nothing, not light, not matter, not information of any kind, can escape. But here's the part people overlook. Outside that boundary, a black hole behaves exactly like any other object of the same mass. If our sun were somehow replaced with a black hole of identical mass, right now, today, Earth's orbit would not change at all. We'd lose sunlight, and that would be catastrophic in its own right. But we would not get pulled in, torn apart, or dragged toward the center. Gravity at a distance doesn't care whether the mass generating it is a star, a planet, or a black hole. The danger of a black hole is entirely about proximity. Get close enough to cross the event horizon and you're gone. Stay outside it, even by a relatively modest margin, and you're functionally as safe as you'd be near any other object of equivalent mass. There's another detail that surprises most people. Black holes, on their own, don't even have magnetic fields. This comes from something physicists call the no-hair theorem, which states that a black hole can be fully described using only three properties: its mass, its electric charge, and its rotation. Everything else about whatever fell into it, its composition, its structure, and yes, its magnetic field, gets erased, swallowed along with the matter itself. Inaccessible to the universe outside, any magnetic field you might detect near a black hole doesn't actually come from the black hole. It comes from infalling matter swirling around it in what's called an accretion disk, material that hasn't crossed the event horizon yet. The black hole itself, in isolation, is magnetically silent. Now compare that to a magnetar. A magnetar doesn't have a sharp boundary at all. There's no event horizon, no single line you can point to and say, cross this and you're in trouble, stay outside it and you're fine. Instead, a magnetar radiates danger continuously through a magnetic field that doesn't simply stop at some convenient distance, and through bursts of radiation that can erupt with effectively zero warning. We already walked through the math. The inverse square law means the danger scales smoothly and savagely with distance, but it never reaches a hard zero. A magnetar 50,000 light-years away already reached out and disturbed our planet's ionosphere. There was no boundary it had to cross to do that. It just did it, from across the galaxy, because its magnetic field and radiation don't respect boundaries the way gravity around a black hole does. This leads to the second major point: predictability. A black hole's behavior, while extreme, is remarkably stable and well understood once you know its mass and spin. Astronomers can model exactly how strong its gravity is at any given distance, exactly where its event horizon sits, exactly what would happen to an object approaching it. There are no surprises, no sudden eruptions, no unpredictable flares. A black hole sitting quietly across the galaxy will, with near total certainty, still be sitting quietly across the galaxy tomorrow, behaving exactly as predicted. Magnetars are nothing like this. Giant flares like the one we covered from SGR 180620 are still not fully understood, even now. Astronomers believe they're triggered by sudden, catastrophic rearrangements of the magnetar's crust and magnetic field, essentially a stellar-scale earthquake. But predicting exactly when one will occur remains far beyond our current capability. SGR 1806-20 had been monitored for over 2 decades before its 2004 flare, producing hundreds of smaller bursts the entire time, and astronomers still didn't see the giant flare coming until the moment it arrived, already traveling toward Earth at the speed of light. There was no warning window, there was no countdown, there was only detection after the fact. There's a real astronomical pairing that captures this entire comparison perfectly. At the center of our own Milky Way galaxy sits Sagittarius A star, the supermassive black hole around which our entire galaxy rotates, with a mass roughly 4 million times that of our Sun. In 2013, astronomers discovered a magnetar named SGR 1745-2900, sitting astonishingly close to it, potentially as near as 0.3 light-years away, roughly 2 trillion miles, making it the closest neutron star ever found to a supermassive black hole. You would think, intuitively, that the supermassive black hole would be the dominant danger in that pairing. It's millions of times more massive. It's the gravitational anchor for the entire galaxy. But researchers studying this system found something telling. The strange, erratic behavior observed from this magnetar wasn't caused by gravitational interaction with the nearby black hole at all. The distance was still too vast for that kind of interaction to matter. Instead, the magnetar behaves unpredictably entirely on its own terms, driven by its own internal magnetic processes, completely independent of the enormous gravitational monster sitting nearby. The black hole, despite its staggering mass, was essentially a quiet, predictable neighbor in this comparison. The magnetar was the wild card. And then there's simple statistics. Dangerous, nearby black holes are exceptionally rare, and detecting one is, in a strange sense, easier because we look for their unmistakable gravitational influence on visible matter. Magnetars, by contrast, are notoriously difficult to detect unless they happen to be actively flaring or pulsing in our direction. Many likely exist in our galaxy that we haven't found yet, quietly sitting in regions of space we haven't carefully surveyed, simply because they aren't currently active enough to draw attention. We'll get into exactly how many magnetars likely exist undetected in the next section, but the basic statistical reality is this. We are far more likely to be surprised by an undiscovered magnetar than we are to be surprised by a previously unknown black hole creeping into our neighborhood undetected. Put all of this together, and the comparison becomes clear. Black holes are honest, predictable, and entirely about proximity. Stay outside the boundary and you're safe, full stop. Magnetars have no boundary, behave unpredictably even to the scientists who study them most closely, radiate danger across distances that make black holes look almost tame by comparison, and have already, on at least one documented occasion, reached across the galaxy and physically touched our planet. That is not science fiction. That already happened. The question we still need to answer is how realistic it actually is that something like that could ever happen at a dangerous distance. And that's exactly where we're headed next. By now, you understand exactly how dangerous a magnetar can be and why that danger doesn't behave the way black hole danger behaves. So it's time to ask the question this entire video has been building toward. Could this actually happen to us? Could a magnetar ever end up close enough to genuinely threaten Earth? The honest, science-based answer is reassuring, but it comes with some important nuance worth sitting with rather than skipping past. Let's start with where we currently stand. Based on everything astronomers have catalogued so far, the nearest known magnetars to Earth sit at distances measured in thousands of light years, not tens. Some of the closest documented magnetars include objects located roughly 9,000 light-years away, others around 20,000 tons, and some considerably farther. Compare that to the distance Dr. Gonsler identified as genuinely dangerous, around 10 light-years, and you can see the scale of the safety margin involved. The nearest known magnetar capable of producing a giant flare sits at a distance roughly 1,000 times farther than the range where real atmospheric damage would occur. Gonsler's own assessment of this margin was direct. He called it, quote, a very safe distance. But here's the nuance. That statement is based on known magnetars. And magnetars are genuinely difficult to detect. Unlike a bright, easily visible star, a non-flaring magnetar emits relatively little light in wavelengths we can easily observe. We typically find them either because they're actively producing X-ray or gamma-ray bursts, the kind of activity that draws the attention of orbiting telescopes built to scan the sky for exactly that kind of signal, or because they happen to be oriented just right for their pulsar-style beams to sweep across Earth. A magnetar that isn't currently flaring, isn't currently pulsing toward us, and isn't otherwise drawing attention to itself, can sit in our galaxy essentially invisible to our current instruments, even at distances far closer than the ones we've already catalogued. Astrophysicists estimate that our galaxy likely contains tens of thousands of neutron stars in total, the vast majority of which we have never detected, simply because most of the galaxy, particularly the crowded, dust-obscured regions near the galactic center, is extraordinarily difficult to survey in detail. Of those neutron stars, if roughly 1 in 10 qualifies as a magnetar, the math suggests there could be thousands of magnetars scattered throughout the Milky Way that have never been observed, catalogued, or studied in any way. Most of them, statistically, are still going to be very far from Earth, simply because the galaxy is enormous and the habitable, life-supporting regions we occupy represent a small fraction of its total volume. But most of them are far away is not the same statement as all of them are confirmed to be far away. It's an important distinction, and it's the honest reason scientists describe our current safety as based on the best available evidence rather than absolute certainty. There's a related piece of evidence that makes this entire conversation feel less hypothetical. Some researchers studying ancient Earth history have proposed that a sufficiently close and powerful magnetar flare, sometime in our planet's deep past, hundreds of millions of years ago, could help explain one of the mass extinction events recorded in the geological record. This idea remains genuinely speculative, and there's no scientific consensus pinning any specific extinction event directly to a magnetar flare. The scientists who first studied the 2004 event from SGR 1806-20 raised this possibility seriously enough to publish it, precisely because the scale of energy involved made the question worth asking. If an event like the one we witnessed in 2004 occurred at a dangerous distance, even once across Earth's roughly 4.5 billion year history, it would already qualify as an extraordinarily rare occurrence on any human timescale, while still being entirely plausible across deep geological time. That framing matters because it reshapes the entire question. This isn't really about whether a magnetar will threaten Earth next week, next year, or even within our lifetimes. The honest scientific position is that the probability of that happening on any short human time scale is exceptionally low, low enough that it shouldn't occupy meaningful space in your daily concerns. But across the kind of timescales geology operates on, hundreds of millions or billions of years, the picture shifts. Stars are born, live and die continuously throughout our galaxy. New massive stars form regularly in dense stellar nurseries, and a fraction of those stars will end their lives as neutron stars, and a fraction of those neutron stars will become magnetars. Over sufficiently long timescales, the locations where these events occur relative to Earth aren't fixed. Stars drift, stellar nurseries shift. The galaxy itself is in constant, slow motion. This is also where the comparison to black holes flips one more time, in a subtle but important way. The supermassive black hole at the center of our galaxy isn't moving toward us, isn't going to wander into our neighborhood, and poses essentially zero direct risk to Earth across any timescale relevant to our species. Stellar mass black holes are exceedingly rare and, like magnetars, mostly far from us. But magnetars form as a natural, ongoing part of stellar evolution, happening continuously throughout the galaxy, including in star-forming regions that, on a cosmic timescale, are not permanently fixed in place relative to our own solar system. It's not that a threat is approaching. It's that the universe doesn't owe us a guarantee that one never will, the same way it doesn't owe us a guarantee against any other low-probability cosmic event, like a large asteroid impact or a nearby supernova. So where does this leave us? Comfortably safe, for now, by every reasonable scientific standard available today. The nearest confirmed magnetars sit at distances thousands of times greater than what would be required to cause real harm. The kind of catastrophic proximity we walked through earlier in this video remains, as far as current evidence shows, nothing more than a thought experiment grounded in real physics. But it's also a genuine, if extraordinarily rare, category of cosmic risk, one that exists quietly in the background of our galaxy's ongoing stellar life cycle, largely undetectable until an object either flares or happens to point its beam in our direction. Unlike a black hole, whose risk to us is essentially permanent and essentially zero on any timescale that matters, a magnetar's risk is rare, but never fully closed off, because the universe keeps making more of them in places we haven't always finished looking yet. And that brings us to the final, broader question this video has really been circling the entire time. Not just whether a magnetar could threaten us, but what it means that something this powerful, this violent, this capable of reaching across the galaxy and leaving its mark on our world exists at all, quietly, as part of the ordinary background of the universe we live in. Step back for a moment from the numbers, the Gauss measurements, the light-year distances, and think about what we've actually been describing tonight. A dead star, something that already finished living, already burned through its fuel, already exploded, already collapsed down into a dense, silent remnant smaller than most cities. And yet, even in death, even as nothing more than a crushed sphere of neutrons sitting in the dark, it remains capable of producing an explosion that outshines, for a fraction of a second, every other source of light in the observable universe, except for the most extreme cosmic events ever recorded. There's something worth sitting within that. We tend to think of danger in terms of things that are active, alive, intentional. A predator, a storm, a war. But the universe's most violent capabilities don't require intention at all. A magnetar isn't trying to do anything. It has no awareness, no purpose, no malice. It's simply matter, behaving exactly the way the laws of physics demand it behave, given enough density and enough magnetic field strength. And those laws, indifferent as they are to anything living nearby, are capable of producing forces that would erase ozone layers, disable planetary infrastructure, and disrupt the basic electrical signals running through every nervous system within a dangerous radius. Nothing about that requires malice. It only requires physics, operating exactly as it always has, exactly as it always will, whether or not anyone is there to fear it. This is part of why we started this video with the claim that magnetars deserve more of your fear than black holes. And by now, hopefully, that claim feels earned rather than exaggerated. Black holes are dramatic because of what they represent intellectually. The breakdown of physics as we understand it. The boundary beyond which our equations stop giving useful answers. They capture imagination because they are, in a sense, the universe's ultimate unknown. But in terms of practical, measurable risk to a civilization like ours, sitting on a small rocky planet orbiting an ordinary star, magnetars are the ones that have already reached out and touched us. Not hypothetically, not in a simulation, in December of 2004, recorded by real instruments, confirmed by real researchers, published in real scientific journals. And maybe that's the most important thing to take from tonight. Not fear, exactly, but recalibration. We spend so much cultural energy fearing the dramatic, visible, cinematic threats. The thing that swallows light. The thing you can point a telescope at and see a silhouette of, even though that silhouette represents something we mostly never need to worry about at any safe distance. Meanwhile, the thing that's actually already brushed against our planet, that's actually disturbed our ionosphere and left fingerprints on our magnetic field, sits quietly uncatalogued in star charts. Most people will never look at, getting almost none of the cultural attention its raw, destructive potential deserves. This doesn't mean you should walk away from this video anxious. The numbers are clear and they are genuinely reassuring. Every known magnetar capable of producing a dangerous flare sits thousands of times farther away than the distance required to cause real harm. The odds of this affecting you, your children, or even dozens of generations after you are vanishingly small by any reasonable scientific measure. This isn't a warning about an approaching threat. It's a recalibration of where real cosmic danger tends to hide. Not always in the things that look the most frightening. Sometimes in the quiet, dark, dead stars that finished living millions of years ago and are simply continuing to exist, indifferent to everything around them because that's what the physics of their structure demands. There's something almost humbling in that. Our entire civilization, every war, every invention, every person who has ever lived, has unfolded underneath a sky that already contains objects capable of ending it all in a fraction of a second, sitting at distances that, by sheer cosmic luck, have so far always been far enough away. Not because the universe planned it that way, not because Earth is protected by anything beyond probability and distance. We have simply, so far, been fortunate enough to exist in a quiet enough corner of a vast and violent galaxy. Every magnetar discovered to date has been far enough away to remain a fascinating curiosity rather than an existential threat. That has been true for the entire span of human history, and based on everything we currently understand, it's likely to remain true for a very long time to come. But it didn't have to be that way, and understanding that, really sitting with how thin that margin of safety actually is when measured against the raw power these objects contain, changes how you look at the night sky. Out there, scattered across our galaxy, are dozens, possibly thousands, of these crushed stellar remnants, spinning, pulsing, occasionally erupting with more energy in a fraction of a second than entire stars produce across hundreds of thousands of years. Most of them we'll never see directly. Most of them we'll never even know existed. They simply sit in the dark, doing what the physics of extreme density and extreme magnetism demands, utterly unconcerned with whether anyone is there to notice. That's the universe we actually live in, not the one with dramatic, visible monsters circling the edges of known physics, waiting at a clearly marked boundary. The real universe is quieter than that, and somehow stranger. Its greatest dangers often look, from a distance, like nothing at all. A faint point of light, an object too dim and too far to draw much attention. Until, every so often, for 0.2 of a second, it reminds an entire galaxy that it's still there, still powerful, and still capable of reaching farther than anything we'd normally think to fear. If this exploration of Magnetars and what they reveal about real cosmic danger gave you something to think about tonight, a like or a subscribe would genuinely help this channel keep producing deep dives like this one. These explorations take real time, real research, and real care to get right, and every bit of support helps us keep going. Thank you for spending this time with us tonight, looking a little more closely at the quiet, dark, impossibly powerful objects sharing our galaxy with us. Sleep well, and the next time you look up at a clear night sky, remember that some of the most dangerous things you'll ever learn about aren't the ones glowing brightly enough for you to see.